Good morning all students. Today in this lecture we study about the design process of synchronous counter. It includes some basic steps, so we go through step by step. What is the design process? First of all, we require the number of flip-flops. How many flip-flops are required for particular synchronous counter? So first one is the number of flip-flop. Number of flip-flop is required as mod m. Mod m is state, that is the m less than or equal to 2 to the power n. N is number of bit for any synchronous counter. So mode is always equal or less than 2 to the power n. That is the number of flip-flops. Next state is state transition diagram. The state transition diagram is a graphical representation of different states of a given sequential circuit and the sequence in which state occur in response to a clock input. Means state transition diagram is the state number of states are acquired in the counter. It means counted by the counter in this sequence. Example for mode 6. It means it has 6 states, that is count from 0 to 6 or 6 to 0 for in case of up and down counter. If we take 0, 1, 2, 3, 4 and 5, that is the mode 6 means it counts 0 say 5. Okay, that is the 6th state. The arrow is going 0 to 1 and then 1 to 0 and then 3, 4 and 5 and then it is repeat to 0. It means it is mode 6. It is itself repeat after number of state, that is the 5. The arrow is indicate the sequence is in this direction, that is after 0 it is count 1 and then 2 and so on. Okay, that is the state diagram. Next one is choice of flip-flop and excitation table. We select the flip-flop for the right, the excitation table for the counter. Excitation table is consist present state, next state and the required input or excitation of the flip-flops. Okay, next one is minimal expression for the flip-flop input. This is minimization technique is used by the K map. We use the K map for minimal expression for the flip-flop inputs. And finally, logic diagram. Connect the input of all flip-flop as per the Boolean expression, which is the output of minimal expression, that is the output of K map. So we take one example for the process of design of synchronous counter. Here we take an example, that is design a 3-bit synchronous up counter. 3-bit means number of flip-flop is required 3, that is number of bits n. Okay, how many states are there? That is mode. Mode m should be 2 to the power n, means 3-bit. It means m should be less than 2 to the power 3, means 8 less than or equal to 2 to the power 3. It count 0 say 7 and then repeat itself, means it count 8 pulses. Okay, it count as 0 0 0 0 1 and up to 7 and repeat itself after 7, that is 0 0 0. Because it is up counter, so it count in increasing order, that is 0 1 2 3 4 5 6 and then 0. Okay, now we proceed for design processor. First of all, we require the number of flip-flop. We have the mode, that is 8 to the power 3 and 8 is less than 2 to the power 3. It means flip-flop is required and that is 3. So flip-flops are required 3. In the design process, first of all, we first thing is the flip-flop. So we require the number of flip-flop is 3. Next stage is state transition diagram. State transition diagram means going from state count from 0 1 2 3. The arrow is indicate that is 0, after that 1 2 and 3, that is the state sequence. Okay, so it is the state diagram for this 3-bit synchronous up counter. Next step is choice of flip-flop and write the excitation table of counter with the help of excitation table of selected flip-flop. Okay, here in this example we select the JK flip-flop. So we write the excitation table of JK flip-flop. We all know that excitation table uh, is a combination of present state, next state and the required inputs of flip-flops. So present state is represented by Qn, next state is Qn plus 1 and the required input, that is the J and K. Okay, that is 0 0 0 to 0, present state going from 0 to 0. We have the J and K is 0 and that is the don't care for K. Similarly 0 1, it is 1 and don't care. 1 to 0, J is don't care and K is 1. And Q for combination of 1 to 1 is J have the don't care and K is 0, that is a fixed value. Using this excitation table, we are write the excitation for the counter. Okay, counter has the three flip flop. See, so we have 3 present state and 3 next state for every flip flops. Okay, so we require the 3 inputs for 3 input for the 3 flip flops. Right here, present state, next state, and the required inputs. Present state for the flip-flop number 1, 2 and 3, that is Q0, Q1 and Q2. Similarly, next state right is for the flip-flop 0, flip-flop 1 and flip-flop 2. And right here required inputs, because we have 3 flip-flops, so 3 inputs, that is the first flip-flop is J0, K1, that is J1, K1 and J2 and K2, that is the input of the flip-flop. So we design the excitation table like this. Okay, in this present state we write our states sequence. In this case, in this example, we have count from 0 to 7. Okay, so write 0 1 2 3 4 5 6 and 7, that is our states, or that is the mode. Next one, what is the next state? After 0 0, the counter is count the or go to state is 1. It means 0 0 1 is next state of 0 0. So we write here 1. What is the after 1? It is going to 2. After 2, it is going to 3, 4, 5, 6 and 7. After 7, it repeat itself, because it is mod 8, that is it count 0 to 7 and after that it repeat itself. So it is next state after the 7 is 0 0. Okay, so now the value of J0, K0, J1, K1 and J2, K2 in the present state and the next state. So first of all we see Q0, that is the present state and this is next state. 0 to 1, see here Q0 is 0 and here is 1, means 0 to 1. Present state going from 0 to 1, we see in excitation table present state 0 and next state 1. For this combination, J and K have value the 1 and that is don't care. So J0 and K0 is here, right here 1 and don't care. Here similarly this process for Q1. Q1, the present state is 0 and the Q1 next state is 0. So we have the J1 and K1. J1 and K1, that is the 0 0. For the 0 0 process we have J0 or K0 is 0 and don't care. So right here 0 and don't care. Okay, and finally for the Q2 is 0 for the present state and the next state is also 0. For this combination present state and the next state 0 0, we have the J or K is 0 and don't care. So right here 0 and don't care. Okay, next one, for this combination Q0 is 1 and Q0 is 0. This is 1 and 0, present state 1 and next state 0. We have the combination for don't care and 1. See here, that is the present state and the next state, that is the 1 and 0. We have the J and K value, that is the don't care and that is 1. So right here don't care and 1. Similarly for Q1, that is a 0 present state and here we can say the next state is 1. For 0 and 1 we have the 1 and cross, 1 and don't care. See here 0 or 1, we have the J or K value, that is a 1 and that is the don't care. And lastly Q2 के लिए, q2, that is the present state, is 0, and q2 is here, next state is 0. For 0 0 we have the 0 and cross. Similar this process, we write the full table of remaining j and k inputs. Okay, this is the most important step for apply the excitation table of selected flip-flop to the excitation table of counter. Okay, next step is minimum expression of flip-flops. Okay, for this we use the k map. Okay, for the k map, flip-flops J2 K2, J1 K1 and J0 K0 in terms of present state of the flip-flop. Present state, that is the Q0 Q1 and Q2 for the all the flip-flops, and we have the output, we have the input, that is J0 K0, J1 K2 and J1 or K1. So we write the K map for the all the inputs of flip-flops. For example, J2, first of J2 we have the three combination variable, that is a q0, q1 and q2, that is a present state variables. Okay, present state variable 3. So k map is consist 8 cell, and 8 cell, that is the we fill the here 0 to 7 we fill the value of J2, we filling the these value where 1 and don't care are exist. Okay, after 3 is 1, 4 5 6 7 all are don't care. So 3 is 1, and after that 4 5 6 7 are don't care. After that we know how to write the boolean expression for J2 is for we have the pair, we have no octet and quad, so only we have the pair. So write for this pair, this is q0 and here is that is q1. So q0 q1 is j2 is equivalent to q1 and q0. For similar we write the k2 uh, in the terms of present state, q1 q2 and q0. Okay, by this process we write all the expression, boolean expression for the or the input, that is j1 k1 in the terms of present state, j0 and k0, and we get the expression for all inputs, j0 is 1, k0 is 1, j1 and k1, j2 and k2, and final state is the draw the logic diagram. Okay, we have the three flip-flops in the counter designing. We know that we have the flip-flops. First of all, can draw three flip-flops jk, j0 k0, j1 k1 and j2 k2. It is synchronous counter, so clock is given, that is the negative triggered clock pulse, that is giving all the flip-flops at the same time. This is the synchronous counter. Okay, next one, what is the input of jk for all flip-flops? See from the minimum expression the input of j and k, j0 and k0 are both 1, so 1 is feed j0 and k0. Similarly j1 and k1 is q0, so q0 is here and connected to j1 and k1. And finally j2 and k2, j2 is q0 and q1 ANDed, means j2 output is come from an AND gate input is q0 and q1, so this is connected to j2. Similarly k2 is also q0 or q1 ANDed, so this is also connected to k2. So student, this is the process of design a synchronous, that is 3-bit up counter. It have many more examples, so all the student please do many and many examples for the synchronous counter. It is very important for point of your examinations. Thank you.